So the next speaker is Dr. Kyoung-Min Kim from PCS IBS, and he is going to talk about topological spin textures via twist engineering. So welcome the speaker and
kind introduction. Yeah, my name is Kyoung-Min Kim, and I'm working here PCS IBS. And first of all, I'd like to thank organizers for inviting me at this wonderful workshop. So today I'm going to talk about my research interest, which is twist engineering of magnet. So let me start. First of all, I'd like to thank my collaborators, former PCS members, and external collaborators for their guidance and significant contribution. So this is a line of my talk. I will first introduce general idea of twist engineering of magnet, and then I will focus on the specific application of twist engineering in each axis magnetic system, and the result is emergence of skyrmion. And the last part, I will apply twist engineering in easy plane magnetic system, and we found that merons can be stabilized in twisted magnet. Yep. So in Vanderwaals materials, we have unique means to control material properties. So Vanderwaals material can be easily isolated in monolayers, and then we can stack them with a relative twist angle, as you can see here. So by using this tear and stack method, we can create moiré polaris, as you see here. So this moiré polaris have some unprecedented unique features. So you see this structure is quite uncommon. So, and that's one. And another thing is that we can control the periodicity of the polaris by adjusting the twist angle. So researchers, so by creating these structures, researchers have uncovered several unprecedented physical phenomena. In metals, people found that some correlated phases can be stabilized, and in semiconductor, some interesting localized excitons have been found. So now researchers' focus have moved to magnetic systems, and in magnetic system, researchers have been trying to observe a nanoscale magnetic domain, which is regarded as a characteristic feature of twisted magnet. So there are two main approaches. So some people are trying to observe this nanoscale magnetic domain structure directly by using some imaging method. And another approach is to measure the consequence of the formation of this nanoscale magnetic domain structure, for example, by measuring this magnetic hysteresis curve. So, as I said, nanoscale magnetic bubbles is the characteristic feature of twist magnet. So we can understand such a structure by considering this mechanism. So the twist introduces this moiré structure. Inside the moiré structure, we can find many different local stacking patterns, and each stacking pattern has different magnetic coupling. So here you see, so here red means antiferromagnetic coupling, and blue means ferromagnetic coupling. Here I'm talking about the interlayer coupling. So because of this intriguing interlayer coupling, we expect that non-collinear order would be formed. So in particular, we should consider interlayer coupling as well. And So if you're familiar with Van der Waals tutorial, you may think that interlayer coupling would be much weaker than interlayer coupling. So maybe this detail would not be important, but that is not true because interlayer coupling can be significantly amplified by controlling twist angle. So the interlayer exchange energy is proportional to the area of the domain. On the other hand, intralayer energy is only proportional to the perimeter of the domain. So if the size of domain grows, then interlayer energy can be much more important than intralayer energy. So in this specific limit, we expect that the magnetic domains are energetically more favorable. So these structures appear in twist magnet in small twist angle limit. So I can say that this mixture of interlayer antiferromagnetism and interlayer ferromagnetism is the key feature of twisted magnet. So theorists are going ahead. So they considered the possibility to convert magnetic bubbles into magnetic skyrmion. So here you see, so in the core region, spins point down direction. In the out of the, away from the core region, the spin points the up direction. So this structure actually resembles that of the skyrmion lattice. But there is no winding texture for skyrmion. So researchers considered other magnetic interaction to generate such a winding texture. So they found that magnetic skyrmion can be stabilized in twisted magnet. So yeah, that's
That schematics, the domain one is always created in the antiferromagnetic domain.
Yes.
Is there any reason why the domain one is always created?
Yeah. Actually, another pattern of magnetic domain can be possible. You mean, yeah, so spin can, in both layer, magnetic domain can appear. Yeah.
Yeah, but the domain one can be existed in the outside. Outside.
Yeah. Right.
Sorry.
Yeah. There's a question.
To explain the common winding question.
Yeah, I think this sentence is not very correct. So this texture resembles that of skyrmion. Yeah, if they have some winding texture. Yeah, I'm sorry. Yeah. So these are what have been known in the literature, and so we may ask this question. So what if there is no DM interaction? What if there is no DM interaction? So can you still achieve some skyrmion in this treated magnet? So the question is what we are going to address in the first part. So this is our spin model. So we consider a simple Heisenberg spin Hamiltonian. We have three terms. First one is interlayer ferromagnetic interaction, and the second one is the single ion anisotropic energy. And the third one is the interlayer exchange interaction. And so without twist, this spin model exhibits a very simple magnetic order, as you can see here. So what if we twist this magnet? Then, as I said, some local stacking pattern appear. And then this local stacking pattern give rise to some complex interlayer coupling pattern. So so there are both ferromagnetic interaction and antiferromagnetic interaction. So because as a result of this complex interlayer coupling, we can expect that some complex non-collinear order will form. So for clarity, I'd like to mention that this complex interlayer coupling is not a general one. So this coupling only appear in this specific material. So actually that is detail of our model. So we solved this model with this numerical method. So we compute this effective magnetic field acting on each spin. And then we subtract each spin vector by this field. So with this procedure, we can continuously lower the magnetic energy to find ground state, magnetic ground state. And actually, this method is quite similar with the stability condition in the energy equation. So, but this method exhibit stronger performance than energy equation. So we can easily finding stable magnetic state in shifting magnet. So that is our primary method. And so as a result, we can obtain this phase diagram at zero temperature. So there are many phases, but I'd like to focus on these two phases. So the first one is magnetic domain phase. So the spin configuration is as follows. So here the bottom layer is exhibit a uniform ferromagnetic order, and on the top layer you see some magnetic domain are formed. So away from the domain, it exhibit the positive polarization, outer polarization, and in the center you exhibit the negative polarization. So on top of that, it will be increase. It will be decrease the interlayer exchange energy. Then we found that another interesting phase occurred, which is skyrmion crystal phase. So here I plotted one magnetic domain. I plotted the in-plane spin texture of the one domain. So this is top layer and this is bottom layer. So so the domain on the top layer exhibits some winding spin texture around the domain. So here, so this is just magnetic skyrmion.
Next question. On the boundary between the white and black regions,
White and black.
is in the same direction or in
I'm sorry, here. White and black. What do you mean by white and black? Can you repeat the question?
You have boundaries between light and black regions on the top layer.
Yeah.
So the winding of the spins in the boundary on the boundaries are indifferent. Have the same helicity or they're different.
Yeah. Here they exhibit the same helicity. Yeah, right. You are right. One question. So you can ask, how such non-uniform texture arise, even though there's not only exchange interaction. So we don't have any magnetic interaction such as Topological interaction or magnetic type interaction. So actually, I got this question from Jonathan, and so we don't have any definite answer yet, but our answer is this. So in our model, in our approach, we found, so in our ab initio calculation method, we can obtain detailed information about exchange interaction, interlayer exchange interaction. So as you can see here, interlayer exchange interaction are not smooth across the Waals polaris. So actually, they show some they alternate from ferromagnetic to antiferromagnetic component. So our conjecture is that magnetic state can acquire some energy reduction by forming wine texture because of these complex interactions. So especially this happens when interlayer exchange interaction are comparable to interlayer exchange stress. So there's so sorry.
Can I ask before we move on? So what's the physical picture in this case? Because the spins are easy axis.
Yeah.
So then what's the picture of the texture? How are they?
Sorry, so right now I don't have any good intuition. So we just conjecture that this complex feature can have some significant crucial role, but so my answer is I don't know.
What happens if you do the anisotropy to 0?
In that case, that's interesting question. So in that case, there's no such magnetic phase, and we only have this phase. In this phase, both layer exhibit non-collinear order. So you would get this phase only.
I think this is a very basic question, but when you say skyrmion crystal, I mean, you have so the mass skyrmion number is, we have a situation where mass skyrmion number is 0 and you have just alternating +1, -1, skyrmion and anti-skyrmion alternating.
So we assume periodicity. So the net skyrmion charge would be non-zero. In our
I see. So it's non-zero, it's also macroscopically large.
Yeah.
It seems that now the skyrmion is static. So there are many the skyrmion lattice in your system. So do you have any idea to move this skyrmion? Because to use the skyrmion application, we have to move the skyrmion.
Yeah, that's a very interesting question. And actually, in other work, so the authors raises some possibility to control, to move skyrmion by exerting some external field. I guess it's not field. I think it's spin torque. Spin transfer torque. Then the position of skyrmion is moved. a little bit, and then it becomes unstable. So it can move to other position, other domain. So by exerting some external stimuli, we can move skyrmion.
Skyrmion hopping.
Skyrmion hopping, yes, right. So, more question, then I will move to the next part. Before that, I'd like to mention that we also studied trial case. So here we also found some magnetic domains. And when we start this project, I decided to measure magnetic energy as well. So whether this state is really ground state or metastable state. So anyway, so we also found this magnetic skyrmion in twisted trilayer, and the magnetic energy of this state is only 1% higher than the ground state one. So I can say that skyrmion crystal in this case has a very good, very high metastability. So also I'd like to mention that here the interlayer interaction is much higher than the interlayer one. So with these two works, I'd say twist magnet is a promising platform for generating skyrmion, even without EM interaction. That's one of my main message. And let's move on to the second part. So yeah, maybe you are not very familiar with merons. So meron is basically a vortex-like spin texture. So away from the core, it closely resembles vortices, but inside the core region, the spin configuration exhibits some out-of-plane polarization. So that's the main difference with vortex, and because of that, meron carries some non-zero skyrmion charge. So its skyrmion charge is just -1 harp. So sometimes meron are called the harp skyrmion. So there are counterpart of the meron, which is anti-meron. So in the core, it points out of applied direction, and it carries also anti-vortex spin texture. So its skyrmion charge is the opposite. So merons have been found in various magnetic systems. So if it was found in magnetic disk or chiral magnetic material, and recently there was a proposal that merons can be created in van der Waals magnet, such as chromium trichloride. So the creation of meron in this system can be very interesting material science viewpoint, and also it can be interesting in this viewpoint. So our question is, can you achieve merons in van der Waals magnet by twisting magnet? That's the second question. So this image illustrates our key idea. So when we twist magnet, we can create these nanoscale magnetic bubbles, and that is what people know. And actually, we find another interesting scenario. So instead of uniform in-plane spin texture, so the twist magnet can have meron and anti-meron pair, which are stable. So in this context, so twist induced the interlayer coupling can be a novel stabilizing mechanism for metals. So again, this is our spin model. I used the same spin model, but inverted the sign of the single ion anisotropy energy. So this model prefers the in-plane magnetization. So without twist, it exhibit uniform ferromagnetic order. Same thing, and this is the result. So we found two magnetic phases. This is the uniform ferromagnetic phase, and another one is magnetic domain phase. This is quite similar one with the EG axis case, and yeah, you see there are some domains, and then in this case, both layers exhibit some non-collinear order. There are some 90 degrees spin rotations. Yeah, so another so this is our main result. So in addition to magnetic domain, we found that fifth magnet can have this stabilized meron and anti-meron pairs. So you see this is top layer and this is bottom layer, and you see meron and anti-meron are formed simultaneously. Actually, these pairs are usually unstable because they usually attract with each other and then pair annihilate. So in normal magnet, they are unstable. However, in twisted magnet, we found that a meron is accompanied by another meron on the opposite layer, and then they are paired with each other, so that they can have this interlayer alignment. Once this interlayer alignment is achieved, then it cannot be changed, because if the core is shifted this way, then it would arise a substantial energy increase. Because so this configuration can be stabilized by the bulk energy minimization. So maybe you can get more insight by watching this video. So I want to play this. Yeah, as you can see, meron and antimeron appear in top and bottom layer. So you see there are 4 merons, but 2 merons annihilate with each other. Yeah, and video is slow. Yeah, finally, in top layer, there are only 2 merons, and bottom layer as well. So this is the lowest magnetic energy state. So we can summarize this stabilizing mechanism in this schematic figure. So the presence of 2 meron in top and bottom layer can act as an energy potential. So they are meron and antimeron cores. So when they are shifted from this equilibrium position, it inevitably arises some substantial energy cost. So this can act as an energy potential to localize metals. So we analyze this stable meron state in more detail. So in twist engineering, twist angle is a very important parameter. So here we thought that twist angle maybe can be used for tuning stability of stable meron state. So here I computed magnetism curve of this meron state, and the red line represents the curve for stable meron state. So you see it shows some kink around here at this field. The stable meron state turns into magnetic ground state without merons. And I calculated this critical field as a function of twist angle and obtained this result. So this, as you see, if we decrease twist angle, then the critical field increases. So which indicates that we can control the stability of merons by decreasing twist angle. So let me summarize my talk. So the take-home message is that twisting magnet can be an effective way to generate topological spin texture. So specifically, I showed that in each axis magnet, we can create skyrmion even without DM interaction. And each plane magnet, we can obtain a stable meron state, which is very unconventional. So that's all. Thank you for your attention.
May I accept some questions from the audience?
I'm still a little confusing about the definition of the meron. So what's the difference between the meron and vortex?
Yeah, vortex means there is no out-of component, right? There's no.
But the vortex in the center, it forces the magnetization towards the top.
Right. I'm not sure. So, Professor Kim, can you help me?
I thought the topological defect is defined XY plane, and then Veron and skyrmion is a topological defect defined in S2 sphere. So if we point the up direction, then let's find the Veron. Enough.
Yeah, I think vortices appears in the XI model. There's no out of plane component. It has only two components, vector component.
Same. They are same magnets. Vortices never the same in easy plane magnet. As long as this easy plane anisotropy is sufficiently weaker than the extreme. But if the easy plane anisotropy is extremely strong, then even at the core, you wouldn't have polarization, right? But if it is easy plane anisotropy is sufficiently weaker than the extreme energy, they are the same.
Thank you.
I found the definition of meron and vortex fluctuating depending on the field, but in my understanding, meron exists as a pair, and the situation where in the bulk the magnetization faces a direction, only one direction. But in your case, direction of relation rotating, boundary. I think so. So I'm confused about the definition of fluctuating. So I mean, so I think this is not meron in my definition.
Yeah. Yeah.
Because the vector rotating, right, far from the center, but meron. Okay, this is just.
Yeah.
Okay, I'm sorry.
Let's go.
But what are exactly theta angles which you consider in this?
Sorry, what is?
You said twisting angles. What are their value?
So you mean what is the twist angle?
Yeah, just because it, as far as I understand, it defines the periodicity of the Kyoung-Min crystal.
Yeah. So the rotation angle.
Yeah.
So the relative rotation angle between top and bottom layer. So we start with an aligned bilayer, and then we rotate one of the layer slightly. That is the definition. The rotation angle is twist angle. The rotation angle. The rotation axis is the outer plane axis, and then the rotation angle is twist angle.
But what are typical values? Which are interesting, the most interesting.
Sorry, that's
He's asking about the value of twist angle.
yeah. So value of twist angle.
Yeah.
I see. So here I used so this corresponds to 1.6 degree.
So the periodicity of your Kyoung-Min crystal is about hundreds of lattice parameters.
Yeah. That's right.
So Kyoung-Min crystal always formed something like this. There are no
There's to my knowledge, there are no study about twisted scale lattice, but I think it is possible to create skyrmions. There's no constraint to honeycomb lattice. I think so.
There any more questions?
I have a question. So your electron part is gas or is something underneath? Are the electrons still there? It's a metal or superconductor, right?
Yeah.
What's underneath?
Yeah, there's semiconductor because there's no alternative electrons, only localized spins exist. Yeah, but I'm also considering to make these things in metals, but then it would be much more interesting.
Yeah, so in your skyrmion, so can you explain us what determines the direction of the winding direction?
I think it's determined spontaneously. So because there's no DM interaction. I mean, there's no interaction to determine the finality. So I think, they are degenerate. So they determine spontaneously.
But once you determine for one skyrmion, all the skyrmion of the same layer should have the same size.
Yeah, I guess so. Yeah, because in that case, the energy will be different if they have different skyrmion number. Yeah, that's my guess.
So if there is no further questions, then I think we may end our session. Also today's talk.